So we have a way of finding the points of our line when we have known values, right? When we have a value like 10, let me get this color here. When we have a value like 10 or a value like -2 over 0, 0, 1, right? We can then use that all within this kind of these equations that we wrote here in order to find what the y coordinate needs to be. However, what we have in code is we don't have those values. We have p1.x and p1.y, p2.x, p2.y. And then we're going to be specifying like an x of -300 and an x of positive 350. So we need a way of actually specifying this more generally, right? Not in terms of numbers like 1, 2, 3, 4, and 5, but in terms of variables like p1.x, p1.y. So what this looks like is the following. If we have this line over here, let's draw another line once again, and let's do something like this. So we can go from -1 to 2, and we can keep going onwards, and I can extend this line a little bit more. Okay? So what we know, right, or the method that we're saying is, okay, if we have 2 points, right, say the points that we know is this one and this one, and we know what the gradient is. If we have 2 points, we can easily calculate the gradient. The gradient is simply this change in y over here over this change in x, right? This delta y, delta x. So I can call this, let's call this m1 is equal to delta y over delta x. Now I'm wanting to find the coordinate at some random point over here, x, and I'm wanting to find its corresponding y coordinate, wherever that might be. Now, what we're saying is that whatever this change in x over, or this change in y over here, let's maybe go in a different color. This change in y over this change in x must be equal to the old one, this delta y, for this delta x. That must be equal to delta y over delta x, right? So the ratio, because the size of the step doesn't matter. Now, if we just put in symbols instead of numbers, let's see what happens. So this delta y over this delta x, let's keep it the same color, right? That, if we say that this is, say, P1, and this over here is P2, right? Or we could say the other way around. It doesn't really matter, but usually we would end up saying that the one later is P2 and the one before is P1. So that delta y over there is equal to p2.y minus p1.y, right? So that delta y is equal to p2.y minus p1.y. And the delta x is equal to p2.x minus p1.x. So we know that that m is therefore equal to p2.y minus p1.y over p2.x minus p1.x. Okay. Now the red one, right? We're specifying some x coordinate, right? So now we're just going to use x and y, right? To say that this is x and y. Those are the symbols. But we could use a and b, banana and pear, whatever you want to call it. We're just going to use x and y here. And what that then looks like, that delta y for the red one is equal to, oh, can I zoom out? There we go. Is equal to this y over here minus, or this y over here minus this y. And this x over here minus this x. So that delta y is simply equal to y minus p2.y. And the x is equal to the x coordinate that we're specifying. The x is all the way over there, but we're really there. X minus p2.x. And now we know that those are equal, so we can make the one side just equal to the other side. So that is equal to y minus p2.y over x minus p2.x. And now if we simply solve for this y, this is the y that we're after. So we need to solve for that y. let's go ahead and put this all now in one regular color. So we have y minus p2 dot y over x minus p2 dot x is equal to p2 dot y minus p1 dot y over p2 dot x minus p1 dot x. If I solve for this, or what could make this easier is if I just simply call this m, right? If this over here, if I just call that m, we're then going to be dealing with far less kind of symbols. So that goes y, p2 dot y over x minus p2 dot x is equal to m, our gradient. Solve for y minus p2 dot y is equal to m into x minus p2 dot x. And then if I solve for that finally, I'm going to get y is equal to m x minus p2 dot x plus p2 dot y. Okay? Now, what's cool here, if you've done this before, you might be seeing, hey, have I seen something like this? If I multiply in this m, I get, let's again mix up some colors here just so we can see it. If I multiply in that m, so I go mx minus mp2 dot x plus p2 dot y, right? I just multiplied the m into these two. This looks very similar to y is equal to mx plus c, right? And all that we have here is that this on the right over here is our c, right? Because our m, right, this is our m over here, and our c, because these two are known points, right? We know where p2.x is and p2.y is. We're looking for this x and this y. So that over there forms our c, which comes to this classic equation of the line y is equal to mx plus c. So the m defines the gradient, and the c simply defines like where it cuts the y-axis. So how high, imagine if I had this line and I just moved it up or down. This is what c would do. M just defines the gradient. But this then gives us a general formula which we can use in code in order to find our line. So let's have a look at that. So in code, this looks like the following. Firstly, let's define a variable for our m, right? Based off of p1 and p2. We know our gradient m is simply let m is equal to p2.y minus p1.y, our change in y, over our change in x, p2.x minus p1.x. Now, if we define a point somewhere else, let's say we're wanting like our x to be, let's use the one that we've used here, right? 250. So if we say, okay, we're wanting our x to be 250, what is our y coordinate at that point such that the gradient remains the same? We can use this formula, which we derived previously. And what that looks like is you can say then let y is equal to m, which is this m, times by x, and then that is minus m times by p2.x plus p2.y. Now that is just simply our c, right? That is our c value coming from there. So we can create another variable to say let c is equal to negative m times by p2 dot x plus p2 dot y. That is the c value. And our y is then m times by x plus by c. And if we now want to simply extend this line, let's move this line over here. So we're going to go line, and we're going to put our, instead of 250, I'm going to put x, and I'm going to put y. And now when that runs, have a look at this. Our line is constantly remaining, right? We're never getting that kind of, right? We're keeping a very consistent gradient. And we're always looking at this coordinate 250. So you can see we're not going above 250. If I now want this to go all the way to the end, right? So think about this. I want it to take up the full width of my page. The full width of my page is at width over 2, right? So the whole width, or the whole page, is width. We're starting at 0. So that means all the way on the right is width over 2. All the way on the left is negative width over 2. So I could define this. I could say let x max is equal to 250. And then I could say something like y at x max. It's a long variable name, but it allows it to be quite useful in regards to understanding it, right? So y at x max is an m times by x max plus c. And now if I'm wanting, then I can put x max and y at x max. And now if I'm wanting it to go all the way to the end, I could do let x min is equal to, oh, wait, x max is equal to width over 2, as we defined, and x min is equal to negative width over 2. And then let y at x min is equal to m times by x min plus by c. And we're going to say line from p1.x, p1.y to x min, y at x min, x min. And now we're going to get our full line that goes throughout the page, right? How beautiful and lovely is that? We can get rid of some of these, right? So now we're drawing unnecessary amounts of lines. We can simply draw a line from x min, y min to x max, y max. So let's do that. Let's get rid of all of these lines. And we can simply say line from x min, y at x min to x max, y at x max. And this will then give us a full line going throughout our page.